Alrighty, we're back again. This is our second video looking at this titration curve here. And just a reminder that we are titrating the strong acid of HCl against the weak base of NH3, and that we have a situation where both our weak acid and our strong acid and weak base have the same concentration. In the first video, we figured out how to calculate the starting pH. That was before we started the titration. And we calculated our theoretical minimum. That's the minimum pH we could possibly reach that we're never actually going to reach. So go back and look at that video first. But in this video, we're going to get straight back into looking at the pH at equivalence point. So remembering that our equivalence point is going to be where our number of moles of acid is equal to our number of moles of base. And we just need to have a little aside here that this is a very useful equation for us at this point, and that our volume needs to be in litres, which is mils divided by 1,000. That's just two little reminders. If we're at the stage where our number of moles of acid equals our number of moles of base, we will only have products essentially, and these are very key ideas. So at equivalence, the number of moles of acid is equal to the number of moles of base, and therefore it's been converted into products. Having a look here, NH3 plus HCl, if we have equal amounts of these, then they've all been converted into our products, NH4 plus and Cl minus. Let's go back and remember the first titration we did, where we did a strong acid and a strong base. So at the equilibrium position for this, at the equivalence point, we had equal moles of these two. So in fact, none of those was in excess. They've all reacted with each other. And we produced this salt and this water. And we recognised that this was a neutral salt. In fact, Na plus and Cl minus, neither of them donate or accept protons from water. So straight away we went and said the pH at the equivalence point here is 7. Going back up to our current titration, we can see that our salt is composed of NH4 plus and Cl minus. You'll note that this is an aqueous solution. It's in water, so I have actually chosen to draw these two ions separately this time. And we should be able to recognise from our prior learning that this is an acidic salt. Right? This does not do anything with water appreciably, but this thing here, the ammonium ion, can donate a proton to water. It's got an extra proton. So let's go down here and write an equation for that. Here's our ammonium ion plus our H2O, equilibrium arrow, this is a weak acid, and we get the proton being donated to water, and here are our products. H3O plus, which makes us pretty confident that we've got our acidic salt, so that's great. So there's two things we need to do to get this point that we want to plot. So we want to plot another point here for our equivalence point. We need to know what the volume is and what the pH is. So we need to know how far across here to come and how far up in pH to plot this point here. So let's start with the volume. Okay, the good thing about this question is that our acid and base are of the same concentration. Oops, that's pretty bad, sorry. So they're both 0.232, and they react in a 1-to-1 mole ratio. So if we have the same concentration of an acid and a base, then we can actually just say the volumes are also going to be the same. Okay, so we've got the same concentration. We know by definition that we're going to have the same number of moles. So if N is the same for both of them, and C is the same for both of them, then V is the same for both of them. So we are going to have 20 mils as our equivalence volume. All right, so that was nice and easy. If these two concentrations are not the same, then we need to go in at this point and do an extra calculation, and that extra calculation is going to involve these ideas and these equations here. Okay, so we'll give you an example of that in another video. All right, so now we know it's 20 mils. We now need to know how far up that vertical scale we're going to go. So what's the pH? We've worked out that it's going to be an acidic pH. So basically what we're doing is we're calculating the pH of a weak acid. And we do know how to do this, but there's one little tricky bit. Let's start with the basic idea here. So the pH of a weak acid, as we know, we need to write a Ka expression for that weak acid. So I've already written the equation below. So the Ka is the products over the reactants, right? H3O plus over NH4 plus. Okay, so we've got the Ka that was given to us in the question. We're going to make the same assumption as we always do. This is x and this is x, so we're going to make that x squared. But this is the tricky one here. Right, so this is where most people go wrong when they're doing this calculation. It is not 0.232. So remember what we've just said is that we started with 20 mils of NH3, and we know we've just worked out that we were going to add 20 mils of HCl to get to the equivalence. Remember we said the concentrations were the same, and at equivalence the number of moles is the same, so therefore the volume is the same, right? We've got the same volume. So we are now looking at a situation when we've added that 20 mils in, which has resulted in this weak acidic salt. So we've actually got 0.232 moles per litre for our original, and we have doubled the volume, right, 20 plus 20, which means we are going to half the concentration. So the products are going to be half as concentrated as the original substances, because they are sitting in 40 mils, whereas our original substances were in 20 mils. So 0.116 moles per litre is the number that's going to go in here, right? So the Ka from the question, x squared, and now we know that it's half the original concentration because of the doubled volume. So if we substitute those numbers in and rearrange and solve for x, x will of course give us our concentration of H3O plus in this case because it's acidic, H3O plus. And then we negative log that to give us our pH, which in this case is 5.09, which is not a bad pH for our equivalence. Right, so now we've got our equivalence point pH, so let's plot that. I'm actually going to use my Sharpie here. So we need to go across to 20 mils here, and then we need to go up to just above 5, so 5.09, and plot our point there. Right, so there's just one more point to go, and I'm going to spend quite a bit of time on this, and this point is the pH at half equivalence volume. Okay, so in this case, half equivalence volume is at 10 mils, right? So we are just trying to find what pH is happening on our curve at 10 mils. So we want another point on our curve somewhere in here. All right, so for this, it's actually quite tricky. In fact, I'm going to make this easy at the end, but I am going to teach you how a certain method that is going to help you if you do get a random really tricky question, and that is going to be the ICE method. All right, so here's our titration. It's NH3 plus HCl goes to NH4 plus Cl minus. And I'm going to go down here, I'm going to go initial, that's my I from ice, and then I'm going to go change, that's my C from ice, and I'm going to go end, that's my E from ice. Okay, so now I've got this little setup like this. Okay, so initial means before I do the titration, how many moles of everything have I got? So N equals CV. So for NH3, I started with 20 mils of 0.232. So 0.02 litres times 0.232 and that is going to give me, I'm just going to bring my calculator over here, 64 times 10 to the minus 3. Okay, I can be pretty clever here if I like, because I know that at this point, at half equivalence volume, I've added, let's put 20 mils in there, I've added 10 mils of HCl, and I also know that my HCl concentration is also 0.232, so N equals CV, etc., which equals 0.01 times 0.232. So it's obviously going to be half this. So it's 2.32 times 10 to the minus 3. These are our moles. Okay, so imagining that I'm at this point, but I haven't yet added them together. So at this point, I haven't actually added them in my mind. So I've got 0, 0, and 0. I haven't made my products yet. Okay, so what did I have in 20 mils of that? What would I have in 10 mils of that? And I haven't made my products yet. Okay, so now I'm adding them together, and I'm going to look at how these moles change. And let's always remember that this is a 1 to 1 to 1 to 1 mole ratio. Okay, so since these react in a 1 to 1 mole ratio, how many moles are going to react? Well, it's going to be the lower of the two. Right? 4.64 moles can't react because it doesn't have another 4.64 to react with. So it's got to be the lower of the two numbers, right? And how is it going to change? Well, that is going to decrease because it's going to react. And the same amount there is going to decrease because it's also going to react. So that's reacting with that to make 1 to 1 to 1 to 1, that many moles of that, and that many moles of that. 2.3, oops, that's 2.32. Okay, all right, so that's our change. So the reactants are going to decrease, the products are going to increase, and in this case, because it's a 1 to 1 mole ratio, they're going to decrease by the same amount that they increase by. So what are we going to end up with? We started with that many react, so that minus that gives us 2.322 times 10 to the minus 3 left over. That minus that gives us 0. That plus that gives us 2.32 times 10 to the minus 3. And that plus that, gives us 2.32 times 10 to the minus 3. So that's what we've got at the end. Now, our next question we ask ourselves is, we need to calculate the pH here. So what have we got that's going to affect the pH at this point here? So I look up here. This is going to affect the pH, right, because it's a base. So this is an important number. This would affect the pH, and it would be really important because it's strong. However, I don't have any of that. This is an acid, so this is going to affect the pH. And this is not going to affect the pH because remember Cl- does not accept protons. So here's what I've effectively got. I've got some NH3 and some NH4+. At this stage, what we're going to do is we're going to write a Ka expression for our weak acid, which in fact we already have from up here. So I'm just going to recopy that. Okay. But this time my calculation is just slightly different. Okay, I do know this. This was still the same. This is given to me in my question. And this time, this number here, my NH3, is going to substitute into here. My NH4+, I'm not going to go X times X this time. This is going to be my X. That is what I'm going to rearrange to solve. I'm going to insert the NH3, remember, NH3 into there. I'm going to insert the NH4+. I'm going to insert the Ka, and I'm going to rearrange and solve for this. Now, some of you may have noticed that this is actually a moles, and what I really want is a concentration. But both of these are in 30 mils, 20 plus 10. So I could divide them both by 0.03, right? And then I could put that number in, and that would be my concentration, of course, which is my square brackets. Okay, so if I now put all those numbers in and rearrange, I get Ka, which is 5.6 times 10 to the minus 10 equals this number here. I'm just going to actually use the moles because it doesn't really matter, and you'll see why in a minute. And I'm going to put these moles down here. And I'm going to put H3O plus there. Okay, so those wonderful mathematicians amongst you will notice that that and that are the same. So at half equivalence, these are always the same. So we can just cancel them out. So now I've got that the concentration of H3O plus equals 5.6 times 10 to the minus 10, and I can just negative log that. I'm just doing that now. Oops, negative log. And that gives me 9.25. That's my pH, so let's come to here. Okay, so half of my equivalence is 10 and 9.25, so that is about there. So that's my fourth point. So now I'm ready to plot my graph. So what we want to do is we want to have a little quick rise at the start. Those of you who did the other one where we started at the bottom, we had a quick, that's a quick fall here, isn't it? We had a quick rise there. This bit in the middle here, we want to go reasonably flat, right? Sorry, I'm just going to try and, this is quite hard to draw here. Right, see, I haven't done that, a very good job there. But reasonably flat through there, okay? Through the equivalence point, we want at least plus and minus 2 pH units to be vertical, like that. And then we want to come down and slope and tend towards that asymptote line, but never touch it. Oops, let me just go along like that. So that's what my curve looks like. Okay, so quick change at the start, flat along the middle, vertical through the equivalence point, and then tending towards but never touching that asymptote line. So that's the main idea, but I just want to very quickly, I know this is a long second video, I want to go back through the half equivalence point, right? This one that we went through at the end. So this ice, this is a very useful tool. If you ever get asked a really randomly bad question, which I will go through with you, but let's say they said calculate the pH after 7 mils was added. What's that pH there? Right, you could use the ice method to calculate the pH anywhere along that curve, and it could be asked. It's nasty, but it could be. So that's one reason I went through it. However, if we go back to this bit where we substituted everything in and those two numbers were the same, let's just go back to here, Ka equals, and we had our conjugate base times H3O plus, and we had our weak acid down there, right? So that's this here, conjugate base, weak acid, Ka, right? So here we are here. Now at halfway, these two are always going to be identical, right? So we can always cancel those out. So if we had to explain that point in words, we would say something like at halfway to equivalence, half of the, what have we got? The weak base has reacted to make equal amount of its weak conjugate acid. So here's our conjugate acid base pair. So in our titration, we started off with NH3. We make NH4 plus. So half of that's reacted to make the same amount of that at this point. right? And then we would relate it to this and go, because these two are now equal, they cancel out, and therefore my Ka equals my H3O plus, and here comes the important bit, negative log this, wrap this one in a big box and put some highlighter on it. This is really important. So at halfway to the equivalence point, your pH always equals your pKa. So if I had a question where they did not give me a Ka, but they gave me a curve, I could come and find, here's the equivalence volume, here's halfway to the equivalence volume, and if I just read off my curve, and that's 9.25, and then that's my pKa. Right, so I can read that off the curve. Okay, that was a lot. Basically, that was a real lot. So well done for persevering. Hopefully this gives some of you a few extra ideas. And those in my class, I'll see you next week. Have a great weekend.